Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First and foremost, thank you very much for joining us. It is a series of MACE talk, MACE technical talk that we have a regular talk every Monday. The topic that I want to discuss with you, share with you today is about model-based design. It's a case study. So my name is Mohd Khair from Universiti Putra, Malaysia. This is the presentation outline that I will share with you. First and foremost, it's about engineering design and control model. We start off with the traditional waterfall model, sashimi model, spiral model, and V-shape model. And then continue to challenges of the traditional process. Then I will talk about model in the loop development, simulation in the loop development, hardware in the loop development. And I share with you one work example, is EPAS system, which is electric power assisted steering system, function and management. So we start off waterfall model, which is the oldest model. It is sequential design process. The process consists of requirements, design, implementation, verification, and maintenance. It was introduced long time ago, 1970s. But you can notice waterfall model, there is no feedback. So that means you have to finish off until maintenance, and then you have to go back to the requirement. You cannot go you cannot go phase by phase. Second model is sashimi model. Sashimi model is an improved version of waterfall model. It consists of requirement, design architecture, development and coding, quality assurance, software testing, implementation, and maintenance and support. The good thing about sashimi model, every phase you can do the feedback. Phase you can do feedback. So, for example, requirement, you can always do the feedback. Development, you can always do the feedback. Quality assurance, you can do feedback. Implementation, so on and so forth. So, waterfall model with available phases, or the waterfall model with the feedback. That's the good thing about sashimi model. Next is known as spiral model. So it is software process. It has 4 quadrants. First quadrant, determine objective. Second quadrant, identify and resolve risk. The third quadrant, development and test. The fourth quadrant, plan the next iteration. The good thing about spiral model, is you can observe, you can see that this is a requirement plan. Second, you can always reach, then you have seen the third quadrant, go to the third quadrant, concept and requirement, and then concept of operation. And then next, you have to do risk analysis, complete your first prototype, requirement, verification, development plan, and again, prototype number 2, you have to do draft, verification, test plan, risk analysis, so on and so forth. Risk analysis, operation. This is, we call it a spiral model. As shown as spiral models, describe a repetitive phase of objective. That is spiral model. Next is, you have seen the waterfall, sashimi, and spiral model. But when it comes into a more complex system, because of the number of parameters increase, so some model may not be, benefit fixed, may not be good for that to solve the problem. So we have the challenge of traditional process, as discussed earlier. Number of control development needs domain-specific model, mode. Function-oriented, example ECU. For ECU is electronic control unit, control development. Model are built in different environment, or different version of the same environment. Model data and interface are difficult to merge. The third one, distribution of electronic features over multiple controllers or multiple platforms. But last, the most important thing is very time-consuming, ineffective, and inefficient. That is the challenge of using three models as I discussed earlier: waterfall, sashimi, sashimi model, and spiral model. Now we have uh, the V-shaped model of the systems engineering process. V-shaped model consists of concept of operation. See this one, requirement and architecture, detail design, implementation, integration test and verification, system verification, orientation and maintenance. And this is verification and validation. You can always do that. So V model is a life cycle process, consists of model in the loop, software in the loop, do the implementation, validation, and calibration and release. So in process of ECU development, ECU or electronic control unit development for automotive, you have to go to the model in the loop, simulation in the loop, and in the loop. So definition of model in the loop basically is full of electrical description of the real physical component. We have to do the functional validation, refinement of one model, and software in the loop, functional validation again, whereby we have to do the test scenario where we generate the C code. And followed by the hardware in the loop, validation of control software in real time with actuators, sensors, and actuator signals. So in automotive application, model-based design has been used in by many car manufacturers. The thing is they have to do the certain project with a smaller team and less time within vehicle program. So to meet these challenges, paper and prototype design methodology move to model-based design. So that means waterfall model, sashimi model, and spiral model may not be, suitable. Whereby the V model is the most, is currently used in automotive industry. And this is few examples of simulating application use the model-based design. For example, GM use model-based design, hybrid powertrain, Gen 5, for transmission, Ford have used it, GM, Toyota, Renault, those have moved from paper to prototype, paper model or prototype into the model-based design. So you can see this is the user stories that I retrieved from the MATLAB simulating website. So the waterfall model against the V-shaped model, the waterfall model, the testing activities continues, but the V-shape, the testing activities simultaneous. Then the cost for waterfall model is high compared to V-shape. From the discussion, it is clear that each model can be used depending on system. Well, I have to agree. Each model can be used depending on system, but we can always choose waterfall. We can always use sashimi. We can always spiral. But now, currently, we are moving towards the V model has been there for some time. But V model that include the model loop, simulation loop, and hardware loop in automotive is picking. So I just want to share with you one example of V-shaped model that I use to develop one of X-by-wire technology. So, you know that X-by-wire, we have steer by wire. We can have brake by wire. But in this particular example, I use steer by wire. So basically, I develop a EPAS system, electric power assisted system, steering system. So the requirement is to have, because since the system, this EPAS system will be used in electric vehicle, so the power reduction is less than 10%, C-type, these are all the requirements, EPAS model. So first and foremost, is that we want to do the reshape model, start off the design, the model, the controller that we want to introduce, and this is the key, the control generation, whereby you choose the right platform and do the rapid prototype, real time, and calibration prototype of the impact system. So you have software in the loop, you have processor in the loop, you have always hardware in the loop. Since that we have a impact system, first and foremost, first we design it to get the model. So this is well, get the basic control design, modeling and implementation. We have a first stage, second stage, and third stage. The first stage is basically to get the model right. We can use white box mathematical model, we can use gray box mathematical model and experimental data. We can always black box full of experimental data. So first stage, measured data, data modeling, behavior of the modeling. Second stage, control system design analysis, do the simulations, mission code. The third one is the mission. For in case of IFAS system, seeing that we have a steering column, the motor top, this is the one that we want to develop, this is the motor system that we install. So in this particular example, this is the model. As I said, model coming from the, can be a white box, gray box, and red box. In this particular example, I start off with the mathematical model. And this is the hardware that we use. This is the motor. Consists of torque sensor, because speed, steering and engine speed, and the sensor and the control module. So first and foremost, develop the model. Start of the steering wheel and torque sensor consists of A, section B, which is consists of motor, C, rack and road, D, the rack and road means C and D. Rack. So next, we translate whatever that we have in this model into the symboling. Consists of this A represent part A, part B, part C. This is E consists of a steering column, B motor, C rod, damper. And next, this is the controller that we want to introduce. Input is the speed and the torque from the driver. And then simulation diagram. We have a road condition, a driver model, torque control model, and we have the vehicle speed, request torque. And this is the diagram for EPAS simulation structure. And again, next, what we need to do is to try to simulate the power steering. We start off a very simple controller, this ID, and you see the reduction of torque, reduction of power consumption. And then we use next we use fuzzy PID. We introduce fuzzy PID to improve the power reduction, further improve. And next we introduce GA PID to further improve PID control. So these part A, part B, and part C still in simulation loop. Still in simulation loop. And then in last we compare power consumption, we get using different controller, and next we choose what the right platform. So we have done the controller, we complete, then we choose the right platform that we want to develop the C code. In this particular example, Z is in CP. This is fuzzy PID that we develop, and process and the loop. This is in this particular example, I use PI62, so the board MX7, because it is 10 to 10. So whatever fuzzy PID that we develop, install into the board. That is in the V shape, this is processor and the loop. So we have the for Hill board, we have the plant model, we have ECU functional model, which is all the PID, we use fuzzy logic, GAPID, GAPID, and this is, in this particular example, we use this space microbox. So this is plant model, steering column, motor, this is the controller. So see that this is a plant model, see plant model, or the plant model that we have, and then this is the ECU functional model, consists of all the controllers that we developed. In this particular example, we have PID, start off PID, we have fuzzy PID, we have GAPID, and then we communicate into this space like protocol. This is process control, order in the loop, simulation in the loop, how we will always go around and modify and want to improve the system. So next, the most important is to determine the lean local lean and can network. But that one is very another important character when you want to choose what the right platform. Okay, this is the last one. This is the last example. Here, how in the loop for this one for ABS, this one for coming from Google Image. So what I want to share with you, basically, for hill development, the plant model consists of power steering, motor, as well as the road condition before we put into the disk space micro box, and you have ECU functional model. We have PID, quasi PID, GAPID. Those are the repetitive work. This one is okay. This one firm. We can get this plant model coming from, as I said, white box, gray box, and black box, and functional model. This is the model base whereby firm, we have this one firm, and we always iterate and modify the ECU, the controller, right? So in conclusion, model-based design is the best execution for complex system. So HEAL is the testing process that has proven to be industry standard for ECU. HEAL, however, has proved to reduce the time between system modeling and implementation of prototype hardware. And HEAL provide virtual test solution and behavior thus providing development engineers method to validate control strategy without needing physical system. Yes, you do not need the physical system, as I showed you earlier. This one, just a disk space to replicate the power string system. So this is last slide acknowledgement. This work is part of program local attachment program that I went through 2005 and 2013, and the advisor by Dr. Azman, Abidin, project coordinator and Razia, that I would like to say thank you to all, especially to researchers, Dr. Babul Salam, Dr. Siti Fauzia, and Dr. Kumarisan, and Dr. Zan. It is an effort. This is a collaborative work. It's a teamwork. With that, thank you very much. Thank you for your time, and thank you for listening.